Hi, for this video what I want to do is show you how to do a two-sample t-test for the difference between means when the data is pooled. And for this one I am going to do hand calculations and show you how to use the rejection region decision rule. So in order to be able to perform the two-sample t-test, you do have to have two different populations that you are trying to compare the means for. And the conditions that must be met is that both samples do have to be random. That helps to control for bias, and the samples do have to be independent of each other where one does not influence the other one. And then either both of your sample sizes have to be greater than or equal to 30, or both of your populations have to be normally distributed. In order to use the t-test, we know that the population standard deviation and the standard deviation of both populations are unknown. That's what sigma 1 and sigma 2 represent. You know the sample standard deviation for both of the populations. So that is what is known. If you know the population standard deviations, then you would run a z-test or a two-sample z-test, and you wouldn't have to worry about the pooling. Okay, so that's the difference between a two-sample t-test and a two-sample z-test, is whether you know the population standard deviation or not. Okay, so once you've determined your conditions are met, then you need to decide if you're going to pool or not pool for a two-sample t-test. And you only want to pool if the population variances are known to be equal. So it will either say in the problem, the population variances are known to be equal, or it might say sigma 1 equals sigma 2. So if it says this, then you know that the population variances are equal. Okay, the degrees of freedom when you pool are found by taking the sample size of the first sample size plus the second sample size and then subtracting 2. So that's how you would find your degrees of freedom in order to find your critical value in order to decide where your rejection region starts. And this is the formula that you will use to find t. It is a very difficult formula to work with, and so if you have technology is probably the easier method with this one in particular, but this is the formula that you're going to use. X bar 1 represents the sample mean of the first population. X bar 2 represents the sample mean of the second population. Mu 1 and mu 2 is whatever difference you're testing. For most beginning stats classes, you will be testing that there is no difference. And so for the most part, mu 1 minus mu 2 is going to equal 0. The only time it doesn't equal 0 is if it says something in there like the difference between the two populations is at least 2. If it said something like that with at least 2, then you would substitute 2 in here instead of 0. So for the most part, you're going to start with that there is no difference, that they're equal to each other. And so it's going to be 0, but it could specify in the problem that there is a difference, and that's the only time this would change. N1 represents the size of your first sample. S1 is the standard deviation of the first sample. It's really important to understand which one represents 1 and which one represents 2. So let's go through a problem with this. A manufacturer claims that the mean cost to operate its car is less than that of its main competitor. You want to test the manufacturer's claim. So you randomly sample 35 cars from the manufacturer and 33 cars from the main competitor. The sample statistics are shown in the table. At alpha equals 0.05, do you have enough evidence to support the manufacturer's claim? Assume the population variances are equal. So when you're given a problem, the first thing that you want to do is look at the information that you have, and you want to go through your conditions and make sure they are met. So the first one, and it doesn't matter what order you put them in, and also with the conditions, I will say that some textbooks have different conditions, so make sure you reference your textbook to see if there's other ones that are required based on your text, because I have noticed through teaching statistics that there's a lot of differences between one author versus another. So the first one is it does say that we randomly sampled, so we do have random samples. Okay. The second thing that you want to look for is, are they independent from each other? The samples are independent because the car is made by this specific manufacturer versus the competitor. competitor are different, so samples are independent. Okay. The next one is your sample size. Either N1 and N2 both have to be greater than or equal to 30, or it has to come from a normally distributed population. So for this one, it does say that N1 equals 35 and N2 equals 33. Both are greater than or equal to 30, so we're good. If this condition is met, then you don't have to check for normal distribution. It automatically applies. If this was not met, then you would look to see, does it say that it's normally distributed? Okay, and then the last thing, this is the one, like I said, that determines whether you should use a 2-sample T or a 2-sample Z, is sigma 1 and sigma 2 are unknown. Okay, again, you will know the sample standard deviation for this. And so notice we have S1 and S2. So we know the sample standard deviation rather than the population. Okay. And then we want to decide whether we should pool or not pool. So we would say that we can use a 2-sample t-test. Okay, and then we want to decide should we pool or not. Okay, and I said pour, not pool, sorry. It's hard to talk and write and think at the same time. All right, so the way that we look to see is what do we know about the population variances? So right here it says the population variances are equal. So we would pool since sigma 1 equals sigma 2 is stated. So again, sigma 1 and sigma 2 just represents the population, and really it would be sigma 1 squared and sigma 2 squared because of the fact that the variances are the standard deviations squared. Okay, so if you know that the population variances are equal to each other, then you can go ahead and pool. Okay. If it does not state whether the population variances are equal, assume that they are not. It's always safer not to pool. So as far as these two options go, not pooling is going to be your safer option. So don't pool if you don't know if these are equal to each other. All right, so let's get into the actual hypothesis test. So our first step is to set up our null and our alternative. Okay, so we want to identify the claim. The claim tells us that, so we're testing the manufacturer's claim that the mean cost to operate its car is less than that of its main competitor. Okay, so we're claiming an inequality statement because it says it's less than, so our claim would be about the alternative hypothesis. So we're either going to support that claim or we're not going to support that claim. So the alternative hypothesis would be that the mean of the first population, and let me establish that since notice that we have a subscript of 1, this is going to be group 1 and this is going to be group 2. So when I put the population mean here, that's what mu represents. The 1 represents the manufacturer. If you don't want to use a 1 and 2, you could also write a subscript. So mu1 is less than mu2. So you could also write this as the mean of the manufacturer, like you could write it in word form. The mean of the manufacturer is less than the mean of the competitor. Or you could say the mu of the manufacturer is less than the mu of the competitor. So if you think you'll get confused by the 1s and 2, just make sure that you understand what you're representing here. Okay, the null hypothesis is always the opposite, so we would say that mu1 is greater than or equal to mu2. Okay, since we're using the rejection region decision rule, we do need to know the degrees of freedom. So the degrees of freedom, remember, is N1 plus N2 minus 2. So N1 is 35, N2 is 33, and then we would subtract 2, and so this gives us 66. So when we go to our table to get our critical value, we will look for degrees of freedom of 66. Okay, so I would draw out my normal curve. Remember that the alternative hypothesis determines the tail of the test. So since it's less than, it's pointing to the left. So this would be our rejection region. Okay, and the rejection region is based on alpha. So alpha, if it's not given to you in the problem, the default is 5%. This one happens to be alpha equals 0.05. If they say at a 5% level of significance, that's the same thing as alpha being 0.05. So the rejection region is based on our alpha of 0.05. So we want to find the critical value that represents this. So what we're going to do is we're going to go to a t-table, and we are going to look on our t-table for a one-tail alpha of 0.05. Since it's left-tailed, we would put a negative in front of it. If it's a two-tail, make sure you look at this. So if it's not equals to in the alternative, you would look at the two-tail. But for less than or greater than, we're going to look for a one-tail alpha, and it's 0.05. And then we would go down that second column until we find 66. And if you notice, 66 falls between 60 and 70. It's closer to 70, so we would just use the value for 70. If it's not on the table, that's what you have to do. That's the disadvantage of using tables, is sometimes your values aren't going to fall exactly on there because they can't put every single number on there. But you would just go to the one that's closest. So the 1.667 is what we would use, and because it's left tail, we would put a negative in front of it. So that tells us that if our, and this is our T0 or our critical value TC, different textbooks use different symbols. Sometimes you'll see T star also. All right, so for our formula, and I'm not going to rewrite the formula because I already had it up here. I'm just going to take and plug our values in. So again, we're using this formula right here where we take x bar 1 minus x bar 2. The mu1 minus mu2 is going to be 0 is what we're going to plug in here. And the reason for that is, remember that we're starting out with this being true. Okay, and so other textbooks will write it as mu1 equals mu2, and they always just use equality in the null hypothesis. The textbook that I currently teach from does the complement of the alternative, and they won't accept this, but other textbooks allow this. And if you rewrite this as a difference, we could say that mu1 minus mu2 equals 0. So that's where the 0 is coming from, is the fact that we're starting with there is no difference in this part here. Okay, and then we would plug in the rest of our values in for each spot. So I'm just going to plug everything in. I have it written down. I'm using this chart right here. So on the top, remember that we would have x bar 1, which is 0.53, minus x bar 2, which is 0.56. And then we really have minus 0, so we don't need that part, but the mu1 minus mu2 is just going to be 0 for this case. In the denominator, and this is where you have to be really careful when you're plugging this into your calculator, it's in 1 minus 1, so I would take 35 minus 1 times the standard deviation of the first sample, the 0.06, squared, plus the second sample size, which is 33 minus 1, times the second sample standard deviation, 0.07 squared. And all of this is underneath the radical. And then we're going to divide that by N1, which is 35, plus N2, which is 33, minus 2. And then on the outside of that, and I know that some textbooks, the formula might be slightly different, so I'm just warning you that there are multiple formulas because they don't make it easy for me to teach. All the different textbooks want to have different things. So it's 1 over N1 plus 1 over N2. Okay, when you're plugging this into your calculator, it's really important that you would put this whole thing under parentheses and this whole thing in parentheses. If you don't have fraction buttons where you can plug it in there, it's really important that you have all of the parentheses. So I'm just going to use an online calculator to plug this in. So I'm just going to plug it in 0.53 minus 0.56. And then I would close the parenthesis, divided by, and I'm going to hit the square root button, and I want to make sure that everything goes underneath there. There's also a fraction button on this calculator. This is just Desmos.com. It's a free online calculator. I like it because I can just put the fractions in, and then I don't have to worry as much about putting the parentheses around the entire numerator. If you can't put it in like this, then make sure that you put parentheses around the entire numerator. Okay, then I would have 0.06 squared plus, and another parenthesis, 33 minus 1 times 0.07 squared. And again, if you put this into your calculator wrong, the whole thing is going to be wrong, so you have to be very, very careful about putting this in correctly, because otherwise you will have the wrong output. So, and then I'm going to do times another square root and another fraction, 1 divided by, whoops, I could have just done 1 divided by 35 instead of doing the fraction button, plus 1 divided by 33. Okay, so then you notice that this value over here is your answer. So again, you have to be very careful about plugging this into your calculator. So negative 1.901 is what I'm going to round it to. I'm just going to round it to 3 decimal places. So we end up with t is approximately negative 1.901. Now, to make your decision when you are doing this using the rejection region decision rule, you use your model like a number line. So basically it's centered at 0. Any t-scores that are to the right or that are positive would go to the right, negative goes to the left. And we want to see where negative 1.901 falls on a number line, and we can see that it falls down here. So this is our t of negative 1.901, and we can see that it falls in the rejection region. It's to the left of this value. Had it been to the right of the value, then we wouldn't make the same, we wouldn't reject. So since it falls in the rejection region, we can say that we reject the null hypothesis. Okay, and then you always want to end by interpreting your decision. So we would say at whatever level of significance, so in this case it's 5% because 0.05 alpha 0.05 is 5%. And anytime it says reject, you're going to say have enough evidence. And then here's the difference is you need to know where your claim is. Our claim is about the alternative. We rejected the null. So we're saying this doesn't appear to be true based on our evidence. Based on our evidence, we support the claim. So we have enough evidence to support the manufacturer's claim. And this is where you just go back up to the problem and restate the claim in word form. So we have enough evidence to support the manufacturer's claim that the mean cost to operate its car is less than that of its main competitor. So we have enough evidence to support the manufacturer's claim that the mean cost to operate, and I can't spell, I really can't spell right now, so let me fix that. The mean cost to operate their car is less than that of their main competitor. So this is a lengthy process. This formula can cause problems if you plug it into your calculator wrong. Like I said, if you don't have a calculator that nicely separates the fractions, that Desmos.com is free for anybody to use online. If you're plugging it into a calculator where it doesn't allow for the fraction bar, just make sure that you put both the numerator and the denominator in parentheses. I did also forget that you would have to put parentheses around this entire part too, in order to make sure that the calculator calculates it correctly, because otherwise it can cause problems. So just make sure that you watch for that. If you plug it into your calculator wrong, the whole thing will be wrong. As always, thanks for watching. If you have any questions, please let me know. If there are additional topics that you would like me to cover, please let me know that as well.